To visualize the problem that we face nowadays, we have drawn this pirate, a very handsome fellow. As you can see, it has freckles. And what we've done, we took this picture, we processed it with the Fast Fourier Transform fast. We added some noise that usually occurs in this type of tasks, and we have transformed it back to the original domain. So from the space to momentum, noise, and back. And ideally, this picture should be the same as the original one. But as you can see, it is not. This is this picture I'm talking about. We have deteriorated the quality of it. There are some artifacts like ripples, and small details like freckles are, one can barely see them. This is the standard way of processing the data also in medical examinations. It is ubiquitous, but it's not best. It's just the fastest that we have nowadays. One can employ a different way, a different mathematical transform than Fourier transform and fast Fourier algorithm to process the data. This is the so-called Kravchuk transform or Kravchuk Fourier transform. This is just another alternative of discretizing Fourier transform. So the principle is the same, it's just different implementation. So the Kravchuk transform, we've done the same with our pirate, but we subjected it to the Kravchuk transform. And as you can see, this image looks much better, much more like the original picture. All this perhaps would not be a very important improvement of quality if we were just going to process pirates, but sometimes we would like to process brain for the search of, for example, small tumors. And as you can see, we would love to have much better quality and much more detailed picture of the brain than what we can get nowadays. Moreover, the complexity of the fast Fourier transform does not allow us to process the amount of data that we would like. As you know, nowadays people would like to learn how the brain functions at the level of neurons. That means the resolution that we need to do that is microns. So we need to slice the brain with tomographic methods on micron scale. That would actually take, say, 10, 20 years to process a single brain with the methods that we have now. So we do see the need of finding different ways of processing this data. So general motivation, so far nice, not too much math, is that we need to process data, and we employ Fourier transform approximations to do that in all kinds of disciplines, science, medicine, engineering. And there are different approximations known to the Fourier transform. For a string of 2 to n values, the discrete Fourier transform needs to take 2 to n steps to do this transform. And the benefit of discrete Fourier transform we can take actually from the algorithm which is called fast Fourier transform that imposes additional assumptions on the discrete Fourier transform but lowers the complexity to n times 2 to n. This maybe does not seem much, but actually it is actually a large speed up in information processing. There is also known quantum version of the Fourier transform, QFT, which requires n log n gates to be used on a quantum computer. However, the lower bound on the complexity of Fourier transform is an open question in computer science. So there is an open question of how fast we can process the data in using something like Fourier transform. Just to recall what the Fourier transform is, are you familiar with the Fourier transform? Yes? Okay, very good. So this is an integral transform, as you can see. It basically processes the data in between two complementary variables, for example, time and frequency. This can be done with an arbitrary continuous function. Basically, we are trying to decompose a continuous function in the basis of plane waves, e2 minus it omega. The key fact behind that is that in this continuous domain, these plane waves, they span a basis. Therefore, any arbitrary continuous function can be expressed in this way, in a accurate way. This is not true anymore if we now discretize the Fourier transform. Namely, we will replace the integral with the sum, and we will consider discretized plane waves. These discretized plane waves are not orthogonal. They do not form any basis in this discrete space. And this prevents us from being able to express in an accurate way an arbitrary function. Of course, the discrete Fourier transform converges to the Fourier transform if we take large number of points and we create a dense sequence out of it. But another limitation that we face using this formula is that if we wanted to compute a fractional Fourier transform, which I will explain in a second, we will be not able to do this using discrete Fourier transform. So why fast Fourier transform became so ubiquitous? It's because it can lower the complexity of the discrete Fourier transform a lot by making an additional assumption. This is a divide and conquer algorithm that can be applied to data which is of specific length, and this has to be the length of 2 to n. So one could not process in an accurate way data of arbitrary length. We always have to take powers of 2 to be able to actually use this algorithm. Often people don't remember about it and just implement it as it is. Well, the benefit is that since these discretized plane waves are periodic functions, they can be computed simply once. We divide the whole interval into 2, and these 2 again into 2, and so on and so forth. So we can simplify our life by computing these periodic factors just once. This is why actually we lower the complexity, by just saving our time, knowing that we don't have to compute this more than once. It will be just the same thing. What is the result? So if we have a continuous function f of t, we expect its Fourier transform to be something like continuous over the domain. But if we use the DFT for finite amount of data, its Fourier transform also should be finite. But the computer, the transform that we employ, actually sees this finite sequence as a periodic sequence, so infinite one. It is kind of multiplied in a computer and computed as if this sequence was just one period of a periodic function. This is not necessarily true. When we collect data when we examine brain and we collect the data, we can't assume that the brain is periodic and extends to infinity, right? We would like to process just this data and nothing else. So here, this domain is automatically expanded to infinity, and under this assumption, we achieve completely different result as it is here. And these are the sources of these artifacts that you've seen on the face of the pirate on the first slide. We would also like to use fractional Fourier transform for a very simple reason. It's useful actually for filtering noise from the data. Fractional Fourier transform can be understood as a partial rotation in the space between time and frequency. The full rotation is the full pi/2 angle rotation, while fractional Fourier transform is just some angle by some angle angle between 0 and pi/2. For those who are specializing in quantum physics, you probably use a lot this transform when you perform tomography of quantum states. This is where actually when you reconstruct quasi-probability distributions like Wigner function, you employ fractional Fourier transform there. Okay, this will explain why we would actually like to have it. Sometimes the data that we deal with are just contaminated by noise, and we would love to implement some kind of filtering, but this is not easy. Instead, we can rotate the data, like in this figure in the middle, by employing the fractional Fourier transform, and then filtering actually becomes easy. We cut out the noise, we employ the inverse transform, and we are happy with the clean data. This fractional Fourier transform has also different applications like data compression, phase retrieval, exploring specific regions of interest, optical signal processing. So in general, this is a commodity we would like to have, and we don't have it at the moment. Quantum Fourier transform is a quantum version of discrete Fourier transform. So this is not anything that we can hope that will help. As you can see, this is exactly the formula that we have used then on previous slides, but it is written in terms of quantum states. So the difference is that all amplitudes are computed in parallel at the same moment. But apart from that, we cannot hope for any speed up in this, or increasing the speed of versus the amount of data that we are actually processing. It lowers the number of operations to n log n, where n is the number of the gates to be used on a quantum computer to process some amount of information. N is the number of qubits involved in that. We should remember that every qubit contains 2 to n classical bits, because qubit is a two-level system. So we process 2 to n bits using n log n gates on a quantum computer. So indeed, it seems to be faster than on a classical computer, but we should remember that here we actually should compare quantum resources with quantum and classical with classical. So we cannot talk about any exponential speed up in case of quantum Fourier transform. So the Kravchuk transform is an old transform. I think it's known since 19th century, invented or established by an Ukrainian mathematician. And this is a discrete transform, which is defined on a discrete domain. So the difference now, it is related to the Fourier transform in the sense that if we expand the domain, we increase the number of points and we make them denser, it will eventually limit to the original Fourier transform. So there is a very strong relation. As you can see, we have a different formula. It looks similar. We also have a finite sum from 0 to s, but actually this sum is really finite, not like previously with the DFT, which was infinite, only shrink to the first period of our infinite periodic function. This transform employs Kravchuk polynomials, Kravchuk discrete polynomials, which exist only on the domain consisting of finite number of points, for example, 5, 6, whatever you define, but only there. There is no assumption that this is just one period of infinite periodic function, just there. This makes this sum really finite and allows us to process finite sequences of an arbitrary length. Unfortunately, in classical implementations in software, it features prohibitive runtime as high as the original DFT. And it is not used in everyday life just because it does not have its fast Kravchuk transform algorithm. Otherwise, it would behave much better. Interestingly, this sum can be mapped onto an overlap of two spin S over 2 states. So actually, we can consider a spin system, a spin of large quantity, not just qubit 1/2, but something larger, a qudit, so spin with many, many levels. And for example, in the SZ eigenbasis, so we have one axis of quantization which defines the eigenstates. So in this basis, we consider spin states. And if we apply a global rotation of this spin in this basis, and then we'll search for overlaps with the remaining basis states, then we will be able to compute the Kravchuk functions. And we will actually use this formula in our approach. Kravchuk functions seem odd. Who has heard about that, actually? But I bet that you've heard about quantum harmonic oscillators eigenstates, Hermite-Gauss polynomials, right? Okay, so Kravchuk is just finite discrete version of them. So as you can see, the first, n equals 0, this reminds the basic mode, Gaussian mode vacuum, basically, of the harmonic oscillator. If we have n equal 1, we have this first excited mode. If we have n2, we have the second excited mode. So this is finite. These are actually eigenfunctions of a finite quantum harmonic oscillator. So our quantum oscillator does not have an bounded energy. Now it has bounded energy. And we consider that system. So this already makes it much more friendly, I'd say. And at least to me, it was very helpful to understand, okay, so these are eigenstates of a finite quantum oscillator. Okay. Funny thing is that these polynomials have additional knob. Unlike Hermite-Gaussian polynomials that are always symmetric with respect to the y-axis, these polynomials can be made asymmetric. As you can see, for example, on the right here, for a specific parameter p 1/4, we can shift them to and in a way zoom in a specific region of interest. This is because Kravchuk functions are polynomials that are orthogonal, but with respect to the binomial distribution. The binomial distribution, as you can recall, this is like a discrete version of the Gaussian distribution, of the normal distribution, and there is a parameter of success in this describing this distribution, and p exactly describes this parameter. So we can choose how these polynomials will be distributed over the domain. This will give us another feature that using Kravchuk transform, we will be able to zoom and focus on the region of interest on the image that we process. Okay, not this one. So you see, as you can see on these figures, Kravchuk transform allows us to summarize. The Kravchuk transform allows us to process finite arbitrary length sequence into correct transformed in the momentum domain. So if we extend the sequence, the transformed sequence will be also larger, but will never expand to infinity like it was before. So it has lots of applications in image analysis with the Kravchuk moments, reconstruction of medical images, automatic identification of tumors, character recognition, error correcting codes, digital watermarking, anti-fraud techniques, anything which actually requires fast processing of data and images. There were already first attempts to employ quantum optics to perform this, and they were based on a planar waveguide, a chip like this. So it's a very small piece of glass chip with waveguides which are equally spaced, and this kind of chip can be easily prepared using laser micromachining. And the number of inputs and outputs decides the length of the sequence that you will process, while the length of the chip decides the fractionality of the transform, whether you perform the full pi over 2 angle or half of it or whatever fraction you like. Each of these inputs is empowered by, or to each of these inputs you inject a photon if you want to encode a sequence. So that employs S photon sources and S detectors behind it, and that you have to know that the sequence will be of particular length, and you encode that you want particular fractionality to be performed. This has been proposed by Atakishev and Vogt as early as 1997, and performed experimentally only recently by a group in Germany in 2016, and the other in Rome, La Sapienza. So this technique, although it makes progress, it is pretty stiff. It does not give us flexibility in changing our mind. What if we want some different fractionality? What if we want some different sequence to be processed? Each time one has to prepare a new chip, and scaling of this technology is also rather poor, because you know how many single photon sources you can have, how many single photon detectors can you have. A single photon detector requires cryogenic cooling, so it's a whole device itself. It's very expensive. So I'd say this is rather limited. And the result we have achieved in collaboration actually with a group of Professor Ian Walmsley, then established in the Oxford University. At the moment they are based in Imperial College. Was to show that you can compute this transform using this setup, this simple setup here. So to do that, you have to prepare specific quantum states as an input, and namely these are photon number states or Fock states, or in other words, eigenstates of quantum harmonic oscillators. So you prepare two states like that, or two-mode superposition of states like that. You impinge them on a beam splitter, and then by employing the newest achievements such as photon counting detection, you read out how many photons came out to the left, how many photons came out to the right. I should mention that this photon counting detection is one of the biggest achievements in technology, in quantum technology. These are really devices which allow you to compute how many photons came in. So this is like a sensor which counts 1, 2, 3, 4, 5, but not 6, 7, and it can really count photons which come into it at the moment in the interval between 0 and 25. So we employ two such detectors, and they give us the result K, for example, K photons came out, or S minus K photons came out. We collect statistics with respect to K and S minus K, and this allows us to compute the Kravchuk function. And if we prepare more complex input states, actually to perform Kravchuk transform of specific input data that we want. All this is based on the so-called Hongo-Mandel interference, one of the key phenomena in quantum optics. This was really the phenomenon first described by Mr. Hong, O, and Mandel in their paper, I think in 57. And what they have noticed is that if we have a beam splitter, are we familiar with a beam splitter? Yes? Okay. Beam splitter is just a, as the name says, beam splitter. If we shine a coherent laser beam onto such device, the beam will split into two. And that's it. This seems very simple, and this is how it behaves with classical light, but quantum light behaves completely in a different way. It features quantum statistics, and it does not split like that. If we impinge two identical photons on a beam splitter, they will always bunch. Namely, they will always exit together. They will be never coincidences. So if I throw two identical photons, there is no possibility that they will go apart. Just one left, the other to the right. They always come together, either to the left or to the right. And this is exactly shown on this probability of obtaining k photons on the left. It's probable to have 0 photons, probability 1/2. It's probable to get 2 of them, another 1/2, but it's not probable at all to have 1 photon per each side. This is the Hong-Mandel effect, the quantum interference, and the assumption is that, of course, this beam splitter has reflectivity 1/2. If we change it, the statistics changes, as you can see below. There are some coincidences possible. That's okay. Nevertheless, some events are more probable than the other. This is the result of quantum interference. Some events are amplified, some are suppressed. And all this can be extended and generalized to multiphoton states of light. So now, imagine that we impinge two identical Fock states, say 5 photons and 5, or 10 and 10, onto a balanced beam splitter, so reflectivity 1/2. What will happen? What kind of events we will be able to register behind such a device? Any, or just some, or with what probabilities? So the answer here is shown on the left upper panel. This is computation for 5 photons on the left, 5 photons on the right, and what is probable. Obviously, by generalization of this 2-photon effect, the most probable events is that all photons come out together. So all photons group and go left, and all photons group and go right. However, the other splittings are also possible, but they are suppressed. That's why we achieve this U-shape statistics. Now, other 3 panels show statistics that is achieved for the situation that we interfere 10 photons with vacuum, or we interfere 5 photons and 5 photons for different splitting ratios. It is only to show you that what we observe behind such a beam splitter, whether it's balanced or not, is very much defined by quantum interference, laws of quantum interference. And this is what we actually need to perform Kravchuk transform. This actually events, this physics computes us these Kravchuk functions that I've shown you before. In practical steps, how to compute for a sequence of data, how to compute the transform. First, one has to prepare a 2-mode superposition of Fock states with amplitudes given by the data. This may be real or complex data, denoted by small xl. So we prepare such a superposition. It's another question how to do it. And then we impinge this on the beam splitter. We employ photon number resolved measurements implemented by transition edge sensors, which are projective measurements on Fock states, and just wait. The probabilities of events behind the beam splitter exactly compute as absolute square of quantum Kravchuk transform. We just have to wait and repeat experiments several, probably hundreds times, as it is usually done in the quantum mechanical experiments. Reflectivity of this beam splitter translates one-to-one to fractionality of the transform. So if the beam splitter is balanced, 1/2, we have full transform. So it corresponds to full pi/2 rotation in this domain between two complementary variables. If this is something lower, then we have some other angle, which can be computed according to this very simple formula. And one can further generalize this result by just playing with these photons and, examining how they interfere. One can actually generalize this result to other systems which have nothing to do with photonics anymore. Since Fock states are bounded Fock states, two-mode bounded Fock states can be easily mapped to a spin system, we can actually understand this mapping on this figure. So how to translate two-mode Fock states onto a basis of decay states of a spin S, where S is the S/2, where S is the total number of photons. And in this way, we can understand then this generalized Hongo-Mandel interference that we've seen corresponds to a rotation of this big spin on its sphere, on the Bloch sphere. So, as it is usually, as I shown before, while Fourier transform is a rotation on the plane, this Kravchuk transform is a rotation on the Bloch sphere. And it's very easy to understand how the input state will transform just by computing its probability or quasi-probability function and displaying it on the Bloch sphere. Are you familiar with Bloch sphere for qubits? That's right. This is a generalization to qudits, so a bigger spin. And for the full transform, pi/2 angle, we simply transform a position eigenstate into some other spin component eigenstate, for example, SI, a momentum eigenstate. So this all follows the analogy and the intuition that we have from the usual Fourier transform, which happens on the plane. Here we exist in a curved space, in a Bloch sphere. All this has been tested using the equipment which was available, which still is available at Ian's Walmsley group. This is a typical quantum optical scheme. It starts right here because we need energy from somewhere. So this is a laser. This laser then pumps a second-order nonlinear crystal, the source of quantum light. It actually allows us to perform spontaneous parametric Dunn conversion process. What it is, it means that a highly energetic photon, shown blue on this figure, impinges on this crystal and spontaneously gets absorbed, and in turn, two photons of lower energy, shown red here, are created. So that in this process, obviously, energy as well as momentum are conserved. Spontaneous parametric Dunn conversion, the horsepower of generation of quantum light. If you hear about quantum light, this is how it's being produced. This is 95 or maybe 99% of cases of how quantum light is produced in all quantum labs wherever you go. The spontaneous parametric Dunn conversion process. There are also other sources being worked out, like quantum dots, but they are very far from being reproducible, efficient, etc. While this kind of process can be called already technology. It's fully controlled. So this highly energetic, it's red. It's a red laser, so it's not really blue. but it's a red laser, pumps our nonlinear crystal, and it produces near infrared photons. So here the frequency is, say, 1800 nanometers, while here it will be 1550 nanometers, standard telecommunication wavelength, what we have in fibers around. These so-called red photons, because they are more red than those which enter, they are split with respect to their polarization, and in this way we obtain 4 modes shown ABC here, C and D here, and in pairwise A and B as well as C and D, they are photon number correlated. This allows us to herald and produce Fock states out of these states, so that we want to, as before, we want to interfere, say, 5 photons with 5 photons. In order to do this, we have to first create these Fock states, and this is how it's done. This is called heralding. We use here the fact that spontaneous parametric down conversion produces each time actually two mode states, and they are photon number correlated. So if I have 5 photons in this beam, I know that I will have 5 photons in this beam. I may have 10 photons or even 0 photons. Nevertheless, I will always have the same number of photons in this beam. They are photon number correlated. This state is called squeezed vacuum, if you were interested, or you heard it on the lecture perhaps. So I herald some number of photons here. I do the same in the arm A. I know how many photons enter my variable coupler. This acts as a beam splitter with tunable splitting ratio. And these two detectors, TS2, TS3, they perform the readout that was shown before. So these are 2 detectors that collect statistics that allows me to compute the Kravchuk function. And of course, everything is analyzed, processed in a computer. And these are the experimental data that we obtained with errors shown. The bars are the theoretical values that we have computed. The dots with the bars shown what the experiment has shown. Various colors corresponds to various reflectivities and fractionalities. So not to bore you any longer with this, we can see that the theory or that the experiment reasonably matches the theory. I'm a theoretician, so I try to see the reality the other way around. Of course, my experimental colleagues would be a little bit puzzled with this statement, but I hope that you will forgive me. We've done more measurements of that kind, but probably this is probably enough for you to see the first slide, and that I will quickly show that this all required careful calibration of this setup and confirmation that at the low power it functions well. This actually deep that you see, this is the Hongo-Mandel deep, and which shows this this deep being below value 1/2 tells us that we have substantially suppressed the coincidences that I spoke before, that no photons go out separately in case we have 2 photons. And let me conclude quickly. Transformation of large data is possible in 1 step if we use quantum encoding, so D-level quantum systems. This was transformation of 1-dimensional sequence, but this can be extended to more dimensional data, 2, 3, as much as you like, by employing other degrees of freedom like polarization frequency. At the moment, we think of this experiment as a proof of concept. It is because preparation of photonic input states for this interference is rather limited. It's technologically limited. However, it is less limited in, for example, superconducting resonators as well as in trapped ions. So there one can think of performing more complex sequences than we have done here. It is interesting, this result, in the sense that we know that qudit-based algorithms allow us significantly lower complexity. This is an old result from theoretical quantum science, but was not appreciated until now, as our standard computers are binary, based on binary encoding for the limitations of semiconductor technology. We don't have these limitations on the quantum platform. There are some other limitations, but we can explore qudit encoding and profit from lowered complexity, algorithmic complexity. My co-authors are listed here. So these are two groups, a group of Professor Ian Walmsley, Merritt Moore, William Clemens, Yilmaz Renema, Steve Goldhammer and Andreas Eckstein, but also there is a group from the US involved, these actually who invented this superconducting photon number resolving detectors. They are the manufacturers and the only one in the world, so they were also involved in this work. This is the group of Seu Nam, and in particular Thomas Gerritz and Ralita. We have applied for patent with respect to this invention, and I would like to encourage everybody to start quantum revolution and trying to implement, create maybe a spin-off and try to implement quantum technologies. At the end, I would like to briefly introduce my group, as I am here to promote Polish science and what can be done in Poland scientific-wise. So currently we are 6. My group is interdisciplinary, as this was my dream to work on interdisciplinary research. So in this panel here, it's my oldest postdoc, Adam. He is a computer scientist and backs up all kind of numerical and simulations. He is also an engineer, so helps with some constructive remarks with regards to implementation. To the right, this is Tom Sturgis. Tom came from Exeter. He is condensed matter physicist. Theory. Below, you can see Monica Mycroft. Monica graduated in Oxford University and came to do the PhD in Warsaw. She's doing theory, but also experiments, in particular in quantum optics, but also on the border with condensed matter, as she would like to take single photons and create single photons plasmons in graphene platelets. Here, this is our newest PhD student, Masoud. He is working on theory and experiment as well. His main goal is to produce a quantum random number generator. And in the middle, this is the postdoc who is coming. He will come in mid of April, Raul Correa from Brazil. And he will also join the research and the boundary between quantum optics and condensed matter towards quantum polaritons. So the research line focuses on 4 bits: nano-optics, quantum optics, numerical tools, quantum information, theory and experiment. Although myself, my background is theory, but I always worked closely with experimentalists, so I thought that maybe it's now time to start experiment. And I am actually helping to develop a laboratory of quantum optics in Warsaw. We got substantial money from Foundation for Polish Science, and we are now able to buy the newest equipment and just work with it, as we did, for example, here. Let me quickly mention my partners in the project. So this is Professor Christine Silberhorn from the University of Paderborn and Ian Walmsley, as I mentioned. And we have also home collaborators who support us in experiments, especially in condensed matter. And We have several enterprises that are interested in our research. We stay in touch with them. And I think that's all I wanted to tell you today. Thank you very much.